A warm welcome to the panel members who are here to evaluate my research work entitled Artificial Intelligence in Predicting the Mechanical Properties of 3D Printed Polymers Using Regression Modeling Technique, which is submitted in partial fulfillment of the requirement for the award of degree of Masters of Science in Artificial Intelligence and Machine Learning from Liverpool John Moores University. This thesis is submitted by Dr. Nagendra under the guidance of Dr. Akendra Kumar P, thesis supervisor, and Dr. Ahmed Kaki, the professor from Liverpool John Moores University. I'm basically a mechanical engineering graduate with post-graduation in tool design and executive post-graduation in AI/ML from IIIT Bangalore and a PhD holder from Visvesvaraya Technical University in the field of application of machine learning in mechanical engineering domain. In the present investigation, an attempt is made to implement the machine learning models to predict the behavior of a 3D printed component, which would be very helpful in companies who primarily focuses on the new product development, that which could either be a new raw material itself or could be any of the new product that they are coming up in their research and development. Pertaining to the same domain, a couple of papers are also being published under my name in reputed journals such as Q1 and Q2 journals, which primarily focuses on the implementation of machine learning algorithms in the domain which is primarily related to the energy and also the mechanical engineering. In this presentation, I would like to take you towards the insight of my research, which is under the title Artificial Intelligence in Predicting the Mechanical Properties of 3D Printed Polymers Using Regression Modeling Techniques. Now, apparently in the content part, I'll be taking you through the introduction, aims and objectives, followed with literature survey or literature review, which is done exclusively from the additive manufacturing point of view and also from the machine learning point of view, followed with the methodology that has been implemented in my current research and also the results and discussions which are being drawn from the experimentation part of this, and also followed ending up with the conclusion and the future recommendations of my present work that I have undergone. Now, to begin with, let's understand what do we mean by additive manufacturing. Additive manufacturing is one common process which has now been very widely implemented across the globe, which tries building a material layer by layer. It's like as simple as how we construct the wall. Initially, we lay a first layer of bricks, followed with the binder, and then the second layer of bricks, binder, third layer of bricks, binder, and then the fourth layer of bricks. This is now called as additive manufacturing. Now, what is getting deposited is, it could either be a metal that is getting deposited metal over metal and then simultaneously building the z-axis, or a polymer over polymer and then building a component along its z-axis. It's basically a 3D printing which is defined in terms of its depth or the height. Now, this particular technique is most often used in the new product development, wherein the tooling cost is very minimal because it's just still as a prototype, not the functional part. Some products are also being produced to a higher quality, which serves as a fully functional part. But however, most of its applications are exclusively limited to the rapid prototyping or just as a prototype. Now, how does this particular machine work? Now, this machine or this particular technique uses the filament as its raw material, and these filaments are basically the thermoplastic materials. It's not thermoset, it's a thermoplastic material which are recyclable. Now, these thermoplastic materials could be the polycarbonate, ABS, PETG, PLA, and many other materials. Now, this is the overall schematic diagram of how the product is visualized or how the machine is visualized. And then this is the technique how the product has now been printed along its z-axis. Z-axis meant saying it's the vertical height of the component that is now being built. Now, having said this, the product quality matters a lot in estimating the price of the product that has been printed through this FDM process. Now, this FDM process is also a technique in additive manufacturing, which is known as fused deposition modeling. This model, it is now extruding the polymer or basically the filament once when it is heated. So the heated filament is now being extruded layer by layer, and now we get to see the yellow part that has now been witnessed in this particular animation or the GIF image. Now, this is the overall, once when we take a cross section of the part, this is how the nomenclature of it is. It's the air gap, that is the density, layer height, and the thickness at which we print. Now, this could be correlated in best way like take a sheet of paper and then start shading the paper with a small pencil or a sharp tip pencil. You take more time in shading the entire paper, but whereas if you use the same paintbrush, you cover it. I mean, you cover painting the entire page with a less time because the width of the brush is larger as compared to the tip of the pencil that we use here. So these are the parameters that we now focus primarily in optimizing the quality or in delivering the high quality product which has been printed through this particular technique. However, the quality of the product is not just dependent on the material that we use, it is also dependent on the style at which we print. The quality, what I meant saying here is it could even be the properties of the material once when it is subjected to a different type of conditional testings. Now, these are the important points that the particular machine primarily requires us to fine tune as its process parameters in order to have a high quality product, highly durable product, which includes the layer height, print speed, extrusion temperature, bed temperature, nozzle diameter, infill density, and so on. Now, if there is a platform at which we can control all these parameters, which is through a Cura software. This is the inbuilt open source software which this particular machine uses, through which it is now possible for us to customize the product. Meant saying, customize the process at which the product is being printed. Either you could print, for example, if you take a cell phone, you can print the cell phone right from the base having this by keeping this as the base. And in case if you still want to build it in a better way, you can treat the bottom as the base of it and then you can start printing it vertically up. Okay, so that selection is completely done by the engineer who operates the machine. So this product at which we built, that is built through this technique, it has its own unique properties. That means to say the strength of this is very dominant along its one of its axis. It's as simple as saying that you can split the bamboo stick along its length, but it's quite difficult for us to bend it along its diameter. So that is the kind of property what these particular 3D printed parts possess. Now, having said this, the property that we are primarily targeting to predict is called as the bending strength. Okay. This ultimate bending strength is the most important feature of the 3D printed part, which helps us in using the product over a longer period of time. It could be, for example, the back panel of the cell phone itself. Now, the back panel of the cell phone, once when you keep opening it up and then closing it up, so it should be a proper fit over a repeated number of usage. So this is a clear cut information about its dimensional stability without undergoing any deviations. So such estimations of the material properties are now being done in the present investigation by using machine learning models without conducting the experiments. Now, by keeping this as an intention, the project is now aimed to develop a robust framework to predict the target variable, that is ultimate bending strength of a 3D printed part produced through FDM process, which would be helpful for the new product development industries, which could reduce their time and expenditure, which is very crucial once when they are in a process of developing a new parts or a new material that has been uh, taken to the next level of productions. With this aim, the objective of the investigation is to analyze the dataset for consistency, like how consistent the data is. Do we have any skewness or the quality of the data is now being checked and then cross-validated to explore the relationship between the critical factors which play a vital role in determining the mechanical or the material properties of the products that have been printed, and then out of that to determine the most influential feature which primarily dominates the overall characteristic of the product that is now being printed, and also to design and optimize the regression based model for accurately predicting the ultimate bending strength, followed with the estimation or the prediction of the accuracy and the robustness of the model that has now been done. Now, With this as the aim and the objective to be executed in the present research, the research is now targeting a data source which has already been published in the Harvard repository. It is already available in the Harvard repository, which is also, this happens to be the initial stepping stone towards the present investigation. This paper was very crucial in analyzing it, so which determines the measurements of mechanical properties under the compressive and the bending load for additive manufactured polymers. Now, this particular data set is owned by Professor, uh, one of the professor who is also a PDF. Now, a small confirmation, this is the link for the dataset. And also a dataset access permission has now been taken by the respective professor, Professor Fron. So this access for the dataset, which is even though available online, official permission was now been drawn from him in the month of June 5th. And since then, the research is now completely focused on the above defined objectives and aiming at how do we get the best effective model. Now, in terms of literature, initially this presentation is aiming to get you introduced to the literatures which are related to additive manufacturing, that is exclusively the process parameters which play a very vital role in determining the strength of the product, and then moving on with that is the ML models which are already being implemented in the same 3D printing techniques. Now in additive manufacturing techniques, so the extreme first left column, what we see here are the desirable outputs. The second column speaks about the references, that's basically the author name, and then the parameters what that particular author has looked into, and then the inference from the paper. Now in the first set of data, or basically the paper which is authored by Wang et al. And An et al. They primarily focused on the desirable output as the tensile strength of the 3D printed product, followed with dimensional accuracy, surface roughness, and compressive strength. So to achieve this, going back to the earlier slides, they have inferred that the layer thickness and the deposition orientation plays a vital role in enhancing the tensile strength, dimensional accuracy, and the surface roughness, followed with the compressive strength of a 3D printed product. Now, similarly, in the second set of papers that has now been looked into, Sood et al. Has given a conclusion that all the parameters of a 3D printer, which is highlighted in the column, that is what we see here and the what we see here, okay, these are the important features which has now been critically been told by Sood et al. From his paper. And moving ahead, there are a couple of researchers who have also given the inferences that a layer thickness and the parameters like slice thickness, build deposition, orientation, layer thickness, road width, raster angle, air gap. So these are a few of the dominant parameters of a 3D printer setting which play a very crucial role in estimating the surface roughness and also the product strength. Now, having said this, to sum up all the papers that are now being reviewed, okay, only a part of a paper which has been reviewed is displayed in the presentation. However, most of the review papers are now being explained clearly in the respective section of the thesis. Now, to consolidate about what has been studied until now, the flexural or the impact strength is, well, that is the ultimate bending strength is the one that we are now looking for. So for this to achieve, all the parameters that are now being ticked, that is marked, play a vital role, which includes the layer thickness, Young's modulus of a material, build deposition, build orientation, air gap, that is the density at which the product is print, and then the extrusion velocity. So these are the most important vital machine settings which play a critical role in developing a product which is having the ultimate flexural or the ultimate bending strength. So having said this, from the literature reviewed, these are the four important key parameters. That is the layer height, infill density, print speed, and then the Young's modulus values are the one which are now being taken for the present investigation. So to validate or to justify why these 4 points are being taken, the literatures which are being surveyed and which are now being demonstrated in the presentation is the one which is now justifying us to, or which stands as a pivotal role in why did we take these 4 parameters for our present investigation. However, this conclusion is also drawn from the primary paper that has now been taken as the reference for the present research. Now, moving on to the machine learning models, which are now being already used in additive manufacturing, which includes the algorithm adoptment of a genetic algorithm by Sung Wong et al. So, which says that the genetic algorithm recommended the optimal setting in the combination with design of experiments. However, these design of experiments have different ways of how we design the experiments, which could be the Taguchi design of experiments, RSM, and other different ways, or the mixture or the mixed factor at which we can design the experiments could also be done in this investigation. And all three papers which we see in the first three rows are are being grouped together with an intention of focusing the process parameter optimizations, and the algorithms which are now being used here is genetic algorithm, simulated annealing algorithm, and then the PSO, that is particle swarm optimizations. So from the paper, so the respective inferences are now being cascaded here. So an iterative approach that finds near optimal solution by minimizing an objective function used in scenario with complex constraints. So these are the inferences which we get from the papers after studying or after understanding the algorithms that are already being used in the respective paper. Now similarly, SVM models and then the random forest models are also being used in the 3D printing uh, product estimation, or basically the feature estimation itself. Now, having said that, in continuation of the same, we have gotten to see a couple of researchers, that is Zhang et al., Liu Hang et al., who targeted on machine learning models which are primarily used in additive manufacturing, and the models that they used in their research were ANN, AdaBoost. So these are the inferences which play a vital role, a valuable role in predicting the mechanical properties across the different range of additive manufacturing materials and the geometrical entities. Now, in this case, I have cited my own paper here, Srinath et al., and I'm also a co-author of it, which is completely speaking about the linear regression model by using Box-Cox transformation, which tells that a higher order polynomial equation had higher level of accuracy that is being measured, and also the multilinear regression followed with ridge and lasso regression, which are now being authored by Ali and Khadir et al., which are primarily used for prediction model, which are now apparently used in the additive manufacturing techniques. Now, moving ahead with the methodology that has now been followed here is, I'll take you to the dataset content of what we have, and then the levels at which the factors are, followed with what is the target variable, and then coming to the flow at which the experiment is now being carried out. Now, initially, as we told, it's not all the parameters play a vital role. We need to give the ranking of the parameters, and these ranking of the crucial parameters is done by using the literature survey. So, from the literature survey of both the ML models which are used in additive manufacturing and also the core mechanical properties of the additive manufacturing 3D printed product, based on that, we have listed the factors, the key factors. These are the factors which is of layer height, which is having three levels: 0.1 mm, 0.2 mm, and 0.3 mm. Infill part density starting from 45 to 100 with a step value of 5. Print speed, which is millimeters per second, unit is millimeters per second, starting from 29 to 50 millimeters per second with a step value of 2. And then the Young's modulus of the different material which is now getting printed in this particular investigation. However, these data sets are already available in the website or in basically the Harvard repository, which has already been discussed in the presentation in the earlier slides. Now, if the response or the target variable for the present investigation is ultimate bending strength, so let's understand what this ultimate bending strength is. So it is It's like as simple as you have a small panel. A 3D printed polymer is the one that you see here in the red color, over which you now start applying a load along its vertical direction. So it's as simple as this. You hold a pen, the 2 point or the two index finger, what we see here is the first 2 points, and then the point where we now have the thumb, this becomes the third point. Once when I start exceeding my loading, the deformation tends to happen. So in case if the material is able to withstand more deformation, resist more deformation, that material has the higher Young's modulus value. In case if we say that if we are trying to test with the glass with a small amount of load, the glass tends to break because of its inherent nature of brittleness. That material has a lesser Young's modulus value. But whereas if you go with the steel has the larger load bearing capacity. As a result, steel has the higher Young's modulus value. Now, mathematically speaking, Young's modulus is the ratio of stress by strain within the elastic limit. This becomes our response. Now, the purpose of doing this investigation is it is to minimize this process of printing the 3D printed part and then testing it as per the ASTM standards to predict or to get the measurable outcome, that is the ultimate bending strength. So we are now trying to minimize this process of printing and also testing in order to get the result, that is the desired result as the ultimate bending strength, by using a machine learning model wherein you can just directly substitute these factors at different levels, so that automatically the machine learning model will be giving you what could be the closest ultimate bending strength of the material that has been printed with different combinations of these particular settings. Now, this is the methodology that we follow here. Initially, the model is loaded, or basically the data set is loaded, followed with the inferences or the interpretation from the data visualization, which could be with understanding the multi-collinearity and also the interdependency of the different factors which could have a higher impact on the ultimate bending strength of the product. And moving ahead in the next phase, we talk about feature engineering. In feature engineering, it is now yet again split into two. One is feature elimination and the other one is feature retention. Now, in feature elimination, we follow the ridge model. Now, ridge model is developed in order to produce a predictive equation at a higher level accuracy. Now, how do we measure the model accuracy? Is through the mean square error and then the R square value of the model or of the outcome from the regression equation that is generated through the ridge machine learning model. On the other end, once when all the features are retained, we use a lasso regression, Box-Cox transformation, and then the higher order polynomial equations based on the literatures that are being reviewed. However, the fine tuning of the model is done with respect to its alpha value and lambda value, which could be helpful in either eliminating or retaining the features, and then once again it goes back to the interpretation of the data visualization. It flows down in the same way, and this process continues until and unless we get the best optimal value of alpha in the lasso and ridge equation and the best optimal lambda for the Box-Cox transformation. So once when we do get the optimal value of alpha and lambda, that's where the model is further propagated into the evaluation matrix, that is mean square error and R square value, followed with the generation of the prediction equation and the final comparison with between the actual and the predicted value. Now, moving ahead, the data set, this is the data set head of what has been getting loaded into the Python library or the Python notebook. This is where we now get to see the first insight of the data, that is the correlation here. Now, in correlation, we could see the Young's modulus play a vital role in having the higher ultimate bending strength. So here you could see the Young's modulus value of close to 3.5 gigapascals, which has a higher ultimate bending strength, which is close to 65 megapascals. So from this plot, or from this particular plot we could say that the value of ultimate bending strength is directly proportional to the Young's modulus value. Okay. And to substantiate that, we could also see the same in the correlation heat map, which has the highest value, second highest value of 0.99, that is Young's modulus measured along with the ultimate bending strength. So this is under the high correlation. However, that doesn't mean that it's always the Young's modulus value which matters a lot. As I told you, printing the part along it's having the base as the larger surface area and also the smaller surface area matters a lot. So that doesn't mean that we are liable, or we have the freedom to have least consideration in setting the machines. No, that's not correct. So we need to have primarily a couple of settings which are very essential for us to generate a better quality product with a higher and durable strength. So in this context, we now start with the feature engineering. That's where the elimination or the retention of the features are there. So as discussed earlier, we have four features. One is the layer height, print speed, infill density, and then the Young's modulus value. So from feature engineering, which is done through random forest and XGBoost, yet again it's been proven that the value of Young's modulus play a vital role in determining the ultimate bending strength. However, we could see a minimum or the least contribution from all the three subordinate factors. The same thing is also noticed in the XGBoost model. You could also see the least contribution from all the three factors apart from the Young's modulus of the material that is being used. Now, next comes the parameter which is a crucial part in feature engineering, that is, do we need to retain all the features or can we start eliminating the features? Out of four, do we need to retain all the four or can we start eliminating one by one in order to have, or in order to reduce the load on the machine learning model? To do that, we have variance inflation factor value, which is determined as 6.4028 for Young's modulus, a layer height with a value of 5.66, infill density of 7.6, and then the print speed, uh, which is measured as 16.8 units. However, from the thumb rule, any value of VAF or any factor which is contributing a VAF greater than 5, it has a least contribution or it could be eliminated. So this is what the VAF purpose is. So as and when the VAF value goes high and high, the contribution of the respective factor in determining towards the target variable or in predicting the target variable gets least. Okay, that is, the contribution becomes minimum and minimum as and when the VAF value keeps going higher and higher. So in this context, so we could directly come to a kind of conclusion that if at all, if we are being given a chance to eliminate the feature, we could eliminate infill part density or infill density percentage. Infill density percentage in the sense, it's how solid the part is. In case if we say it is 100% infill density, it's absolutely 100% solid. In case if it is 50% infill density, that means to say 50% of the volume is filled with the polymer and the other 50% is left open. But however, from the subject matter knowledge, it is very evident that the density of a part plays a vital role. For example, let's say that this is the solid panel what we see here. This solid panel, it becomes very difficult for us to bend it. But whereas if the same solid panel is replaced with a zigzag pattern or any particular pattern which is slightly hollow, under that case it easily deforms. So it's clearly, even though the VAF value is maximum of 7.66 for infill density, from the subject knowledge it is not recommended for this feature to be eliminated. However, print speed plays a minimum role in the contribution towards the ultimate bending strength of the product. So however, this could be eliminated. So this is a graphical representation of the VAF value for the respective parameters. Now if given a chance to eliminate a feature, then we'll be starting eliminating the print speed first, and in case if there is no chance to eliminate any of the feature, so that's where we'll now be switching over between the two machine learning models, which is Ridge and Lasso. Now in the present investigation we have used, a Ridge model has been used And the order of equation that has been generated here is a single degree equation, and the features that are being selected here is three, and what are those three are Young's modulus, layer height, infill density. Similarly, the second machine learning model which we also used is the lasso single order, wherein none of the features were eliminated. So all the four features were retained in both lasso and the Box-Cox transformation, and then the second degree higher order polynomial equations. So what are those four? It's the Young's modulus, layer height, infill density, and then the print speed. Now, having said this, the residual histogram uh, after the analysis between the training and the test data, which is at a split ratio of 80 to 20, we could see a slight skewness towards its negative in the initial stages of the training data, which is clearly telling that it is slightly, the model is slightly over predicting the result. And if you see the residual histogram of the testing data set, it is slightly skewed up towards the positive side, which is slightly under, which leads us to a conclusion that it is slightly under predicting the value. This was our first ridge model, wherein the factors which we used there were three out of four. Only three were selected in this ridge model. And then moving on to the lasso model. Now here you get to see a complete skewness, which is dominant more on the negative side. You could see a more skewness on -2. The data set is it's largely skewed towards the negative, which is a clear evidence that the model is over predicting the value in the training data, and also in the testing data it is slightly towards the positive value, which is on the under predicting. Now moving on with the next Box-Cox transformation with the optimal lambda value, we get to see the skewness similarly, which is slightly following that of the lasso model. And then the higher order polynomial equation is the one uh, which is having the equal distribution towards the left and the right for the training data, which is neither over predicting nor under predicting. So this is where we now get to see that the higher order polynomial equation or the regression equation generated, it is now predicting a value which is very much closer to that of the actual value. Now let's see how this prediction is happening, and also let's see this, why do we see this imbalance in the residual histogram due to this lasso model in the regression equation in the next upcoming slides. Now, moving on to the evaluation stage of these machine learning models that we have used here. The first is the ridge model, which is of a single order polynomial equation. The features considered were three, and then the mean square error for the training and the test data were 5.172 and 4.405, and then the R square value was it's 98.3% and 97.54%, with the optimal alpha value of 1.6508 for the ridge model. Similarly for the lasso model. Now, as I told you, there is a drop. There was a drop in the mean square error value as and when we moved ahead in the ridge model, lasso, Box-Cox, and higher order polynomial equation. So this is where we get to see the higher order polynomial equation had a minimum mean absolute error value, followed with the residual distribution of each model, wherein this is a slight unbiased distribution what we see here. And the regression equations which are now being generated from the experimental studies, the ridge model single order equation, that is ultimate bending strength, you could see the coefficient intercept value of 6.446, and then the coefficient of y represents the Young's modulus, LH represents the layer height, and then ID represents the infill density. So these are the coefficients for these three factors, and this happens to be its intercept value through the ridge model. And through the lasso model, as I told you in the earlier slides, the data set was completely skewed on one side, that is towards the negative. That is because the coefficient for the other two parameters, even though the lasso model had selected 4 parameters. That is, in feature engineering, none of the features were eliminated in lasso model, but still we don't get to see the other two important factors, that is the layer height and the print speed. The reason for that is the coefficient for those influencing factors is 0. So anything multiplied with 0 is 0. So that's the reason why we don't get to see the other two factors here. We see only 2 out of the 4. And this is the reason why we get to see the skewness towards the left, which is clearly the over predicting model. Now in Box-Cox transformation, this is the equation what we get here with the optimal lambda value and also the higher order polynomial equation. This is where we get to see the order to the power of 2, that is layer height to the power of 2, followed with Young's modulus to the power of 2, having the negative coefficients and then the positive coefficients here. And the intercept value for the higher order polynomial equation is minus 3.69. With these equations being used to predict the ultimate bending strength, this is our result. So what we see in the first column is the actual ultimate bending strength measured in megapascals by using ridge model. That is, once when we do substitution here for the respective machine settings, the model predicted a value of 43.270 in ridge, and then in lasso the same input parameters were being kept, with which we now got a reading of estimated reading or the predicted ultimate bending strength of 43.106 and Box-Cox transformation of 44.49 and 44.87. So these are the same settings for the respective experiment number, with which we are now able to predict 4 different values. We are able to predict 4 different values with 4 different machine learning models that we have generated here, out of which you could clearly see that the value of 44.87 is much closer to 45 as compared to the other 3 columns. So this is clearly evident that the model is it's neither over predicting nor under predicting. As a result, we get to see the closest prediction or the best model which is predicting the value very close to the actual is the one that has now been recommended here. And then if you get to see the comparison between the actuals and the predicted, so this is where we get to see there is a huge difference between the lasso model and then the higher order polynomial equations here. So this bandwidth, it remains common across the entire length of the data points that we now measure. And moving on to the error loss, or basically the percentage error, what we now get to see between or measured between the actual minus predicted divided by the actual expressed in percentage. We get to see the ridge model having an average error of 5.10 for the present investigation, and then the lasso model having an error of 4.83, a Box-Cox transformation of 3.05, and then the higher order polynomial equation which is less than 1.5, that is 1.46%. So this is where we are now in a stage to conclude that the higher order polynomial equation which has now been developed in the present investigation for the given data set is having the highest accuracy in predicting the ultimate bending strength of a 3D printed model, which could be having or which could be using any different material, which is having a Young's modulus value which is specified between the bandwidth of the Young's modulus value used in the present investigation. Now, to conclude here, the Box-Cox transformation and the higher order polynomial equation demonstrated superior performance in accurately predicting the ultimate bending strength value. However, the ridge model and the lasso model also gave an effective contribution in predicting the value, but measured in terms of accuracy, the higher order polynomial equation, predicting using the higher order polynomial equation is matching to that of the actual value. Okay, while the higher order polynomial regression equations achieves the best results in terms of accuracy, Box-Cox transformation provides a good balance of simplicity and performance. Ridge and lasso models, though slightly less accurate, But however, the computational time which could now be taken is very minimum for the lasso androids. But whereas since we go with the higher order equations, the computational time is slightly on a higher end. Now, moving ahead with the future or the further recommendations, this research, as it's an interdisciplinary research, and as the data set is completely stagnant here, it's an offline data. So, as a scope of future implementations or the recommendations, we could incorporate a dynamic adjustment parameters. So, as and when the parameters are very dynamic rather than the stagnant parameter what we have used here, it could be made available that the prediction of the target variable happens instantaneously by using the Box-Cox transformation or a polynomial equation with a higher order, higher degree. And then for practical perspective, the same investigation could also be used in automotive sector to optimize the tire replacement schedule and also to ensure that the passengers are safer enough to avoid the accidents due to the poor grip between the road and the tire. And also the same approach could also be extended in interdisciplinary studies such as the consumption of the electricity, consumption of the water sources, and also predicting the climate conditions. So these are the multidisciplinary or the interdisciplinary parts at which the same investigation could be taken ahead. Now, moving on to the appendix, which has now been the Turnitin report, that is the similarity index. For my present thesis, I have encountered a similarity index of 4% through the LJMU Canvas report, and then this happens to be the official formal approval letter from my thesis supervisor, which is acknowledging the or which is basically permission towards the submission of the report. And at the end, I wholeheartedly thank my thesis supervisor, Dr. Akendra Kumar P, and the professor of Liverpool John Moores University, Dr. Ahmed, for their special contributions and their detailed insight and giving us an insight of how the research is to be conducted, on how the models are to be implemented. With this, I would sincerely thank the panel members for your patience in listening to the work that has been done here. This is just a small attempt. With this attempt, I have taken ahead the present investigation in the form of the paper, which is in the process of submitting in the QN journal under the affiliation of me as the LJME student. That could take a couple of time here because since I very closely completed the project, I am in the process of formatting the data as per the requirement of the respective journal. So definitely a chance is very clearly evident for us to have a proper uh, publication of the given document here, which is a complete interdisciplinary, that is the implementation of machine learning in core manufacturing, that is additive manufacturing. So with this, I would once again thank the university panel members and also my friends, everybody as such who have contributed me very effectively and who have helped me a lot in reaching the stage. And I thank you all. Thank you.